It's my pleasure to introduce our next keynote speaker, Alexander Wissner-Gross, who's a scientist, inventor, and entrepreneur who's done more interesting things than I'm going to be able to list here in a moment. He's currently serving as an Institute Fellow at Harvard University at the Institute for Applied Computational Science. He's also a research affiliate at the MIT Media Lab. His background is quite diverse, but you see the word physics up there. He has a PhD in physics from Harvard, where his thesis on programmable matter, ubiquitous computing, and machine learning was awarded the Hertz Doctoral Thesis Prize. And in the recent past, he has achieved a lot of attention both in the intellectual community and in the broader media for his hypotheses about the relations between causal entropic forces and general intelligence. He had a TED talk on related ideas, which has been viewed something like 1.5 million times. So now we get his views on the nature of general intelligence, the relation to physics, entropy, and so forth. I'm sure there will be some interesting questions and discussions following up this presentation. So,
awesome. Thanks so much, Ben.
Yeah.
Can everyone hear me? Great. Well, let's make this as interactive as possible. Thank you for having me. It's really a pleasure to be talking to AGI enthusiasts about this topic. So as Ben mentioned, I'm a physicist. I'm also a computer scientist. I'd like to think a lot of my work is influenced by traditions on both sides of the physical-digital divide. And I'll be talking for the next hour and a half about the physics of artificial intelligence. And so as a physicist, it's sort of a cultural thing, one is always taught to ask about physical limits and also about observables. Observables are incredibly important. So as a physicist, I can ask myself the question, so I was speaking with a number of you earlier about sort of the origin stories of this type of approach to AGI. It's very natural to ask, what are the physical limits of artificial intelligence? And from a physical perspective, it's very natural to examine time-like limits to AI and space-like limits to AI. So I'm going to devote the majority of this talk to exploring time-like limits to AI, and a bit at the end, if there's time, to space-like limits as well. But most of my recent work has been focused on time-like limits to AI. So this is an analogy that should be familiar to many people in the field, sometimes attributed to Dijkstra, but Dijkstra was hardly alone in this concept. So to abuse a quote from Dijkstra, the question of whether machines can think is about as relevant as the question of whether submarines can swim. So the way I think, helpful or not, choose to interpret that notion is, it's always important to understand phenomenologies before you aspire to understand mechanisms for complex systems. It's interesting to perform a sort of thought experiment in the history of artificial flight. Could we have accelerated the onset of artificial flight in our civilization if we had had a greater focus on the physical phenomenology of flight earlier on, rather than the mechanisms of flight? It's always very tempting to try to imitate mechanisms from biology, from other segments of the existing world, because these are the examples that we have in nanotechnology, in artificial flight, in artificial intelligence. But I think history, at the end of the day, does try to teach us that understanding the physical phenomenology of a complex system as early on as possible is a very powerful meta approach to trying to recreate phenomena that we observe in the natural world. So I pose this as a question, more rhetorically than anything else. Instead of trying to ask, how can we fly like birds, maybe we should have been asking earlier on, what is the physical phenomenology of flight? For example, understanding gliding. And then by analogy, perhaps we should devote a greater emphasis, instead of just asking, how can we build minds, to perhaps an easier question, which is what is the physical phenomenology of intelligence? And what I mean by that is if you have an intelligence in a physical system, so this is an embodied intelligence, what are the physical artifacts? What are the physical processes? What are the physical imprints that an intelligence leaves on an environment? Can we describe the physical impact of intelligence, whatever that is, in terms of physics? I saw a question back there, and I promised to make this interactive, so go ahead.
Right, so I was going to see whether you really wanted it to be so or not. So I was going to rephrase what you just said in a different way and see if you still agree with that.
don't want it to be interesting.
So my understanding of the whole bird analogy is that it doesn't have to do with physical phenomenology, but that you need to understand the principles behind what's going on. Those may be physical, they may be computational, they may be other kinds of things. And one of the best ways to understand the principles of something is to understand systems that exhibit those principles. So that studying birds is important. The question is, what are the level of generalizations and how deep are the principles you get out of it? So if you view it that way, then it doesn't say you shouldn't study birds, you shouldn't try to replicate birds. It just says you need to understand the right depth of principles to derive from them in order to be able to apply that in other technologies.
So the question is, don't we want to understand principles rather than just saying we want to understand phenomenologies? I completely agree. So I think we're saying the same thing using slightly different language. What I'm trying to articulate here is, let's understand the physical principles, physical phenomenologies underlying a complex system before trying to duplicate mechanisms observed in the natural world. And I think it is important to draw a dichotomy between the principles and the phenomenologies and the underlying mechanisms. Mechanisms could be highly idiosyncratic, they could be specific to one implementation of a general process. There are many ways to achieve artificial flight and natural flight, but there are relatively few ways to say, create lift in a hydrodynamic system. And what I'm saying is that it's important to try to understand the physical processes and phenomenologies first, before spending too much effort trying to exactly duplicate mechanisms, if that makes sense.
I don't want to extend this, but you often can't get that full understanding because you've tried to replicate, and in the replication you often understand the principles better, and you understand what aspects of the system really matter, what don't, particularly when you're moving to a different technology.
Right.
So I don't think it's quite as simple a dichotomy that you can't afford to try to do all your understanding before you try to replicate.
Agreed. There's absolutely feedback loop. And so what I would propose is to try to invest more energy, more resources earlier on in understanding general principles, physical principles, instead of just studying mechanisms. So I think we're in violent agreement. So if you take this sort of culture that we should try to understand the physical phenomenologies of complex systems as early on as possible, so what does this tell us about AI? So I thought that morning tutorial was very instructive in that sense. So sort of as a hobby for the first few years of this, living in the world of physics, the world of computer science, I thought it was instructive to sort of keep my head to the ground and look at a number of developments that we've seen over the past few years and note potentially a very deep thread connecting them. So I'll start with games first, since the morning tutorial mentioned Go playing. So I thought it was very interesting that in the discussion, there was so much discussion of the mechanisms of Go and Monte Carlo tree search, Mogo, which was the 2006 Go player that got so much attention. There was so much discussion, I thought, of the mechanisms by which Go is playing, but not actually the take-home lesson that I think we should be deriving from the success of Mogo and then successor systems. So let me speak first a bit about that. What's really remarkable about Mogo and these MCTS, Monte Carlo tree search systems that for the first time are competitive with humans at Go playing? So at the courses level, what these Go playing systems are doing is they're considering all possible legal next moves, and then they're doing a Monte Carlo tree search from those next states out to an end of a game, and they're looking to see, okay, so maybe I'll have on the order of 100 possible legal next moves, and for each of those, what fraction of the time, if I were to play a random game against a random opponent, with pruning supplied by MCTS, would I end up in a state where I win? And at a course level, the approach is as simple as that, nothing more complex, everything else is more or less pruning. So taking a step back and saying, hey, wait a minute. So this game, Go, that everyone, when Deep Blue beat Gary Kasparov in '97, everyone thought Go would be sort of this grand challenge for AI. Why is this grand challenge falling to what is essentially just evaluation of every legal next move and then checking to see what fraction of the random games that can be played, if it's, say, greater than about 80% or so, resulting in a win? How could such a simple process, a simple algorithm, be finally overcoming this barrier? Computational limits aside, the algorithm is so simple, this is something we could have been doing decades ago. So I would call that hint number one, that there's something profoundly interesting, and maybe this is a hint as to a greater phenomenology of AI, that there's something profound about looking at possible actions. So many of us, from a control theoretic perspective, would call this a policy. There's something profound, maybe, about looking at possible legal actions in a control policy, and then evaluating, Monte Carlo style, a large number, as densely as possible in path space, of paths that our universe can unfold along up until some future time horizon. It's a very coarse observation, but I think what's profoundly interesting is several other fields seem to be converging on a similar concept. So again, lesson number one there is there's some sort of, I would say, profound insight emerging from the success of MoGo and its successors as to choosing next actions that will leave open the maximum number of possible paths. In the case of MoGo, it's paths to winning. But my claim is going to be that this is actually an artifact of a more general principle. So second example, in cosmology. So this may be a bit further afield for this particular audience, but a major outstanding meta problem in cosmology for the past 10 to 15 years has been the anthropic problem. So why do we live in a universe that has the properties that it does? And a common anthropic answer to that question is, we live in a universe that has the properties that it does, because if it didn't, we wouldn't be able to exist to ask the question, why does the universe have the properties that it does? And one of the most successful approaches for addressing the anthropic principle is Raphael Bousseau's causal entropic principle, which holds that universes that create the maximum amount of entropy over the course of their lifetime, clipping out certain inconvenient portions of the universe, like black holes, which are causally disconnected from the rest of the universe, tend to reproduce certain critical values that we observe in our own universe, such as the cosmological constant. And incidentally, one of his more interesting conclusions, I think, was this notion that the largest source of entropy creation in our universe, again, clipping out black holes, is starlight scattering off of interstellar dust. So he was able to arrive at a number of cosmological parameters that are within a factor of 2 of the ones that we observe. Now, I would say that this notion that maximizing causal entropy creation for certain definitions of causal and entropy is also, I would say, sending us a signal from the cosmology community that there's potentially some sort of deep connection between causal entropy creation and intelligent observer concentrations. So a normal anthropic approach to trying to derive from first principles the various cosmological parameters that we observe would be to say, okay, so twiddling this knob here for this force constant and twiddling this knob here for this force constant, which combination of these knob configurations would result in the largest concentration of intelligent observer concentrations who are able to ask these sorts of questions? And I think what's so important about this development in cosmology is, for the first time, it provides a firm, either thermodynamic or information theoretic, depending upon which school you come from, foundation for formalizing this question. No longer do we need to define intelligence or to define what an intelligent observer is to ask these cosmological questions. Instead, we have reasonably rigorous thermodynamic or information theoretic quantities that we can, as Feynman and his thesis advisor used to say, shut up and calculate with. So I would say cosmology is also providing some hints to us that there may be some profound connections between causal entropy creation over the course of an extended period of time and intelligence. And finally, I sort of couldn't do justice to the slide without at least alluding to developments in planning in AI. So just as a sort of an example here, I have a PR1 from Willow. Yes, Joshua?
Are you going to elaborate on the causal entropic principle?
That's the rest of the talk.
Okay, good.
So this is the last bit of prelude. So as one example, the almost ubiquitous use now of rapid traversal of random tree type approaches, RRT approaches in path planning, where in a certain sense, if you squint at RRT, it really is an algorithm for trying to maximize the weight of a branch in a spanning tree rooted at your current universe state. So to make Joshua happy, I'm going to move on to the next slide and point everyone to a paper that we published last year in Physical Review Letters, where we think for the first time we've unified many of these disparate threads across domains, as well as many others that I don't have time to allude to, with a new principle that we term causal entropic forcing. Now, as with many advances in AI over the years, this one does not live in isolation. In particular, I would like to credit Polanyi and Klubin's really courageous work on empowerment. And I can speak more about that in Q&A if people are interested, but in many ways this draws upon empowerment and takes many of its concepts to the next level. So how do we formalize the connection? So we've seen, I would say we've seen examples that there are threads that somehow connect this idea of maximizing causal entropy. You could express that as keeping options open. You could express that as capturing possible futures. There are many ways to express it qualitatively. But quantitatively, it turns out that there's already a lot of machinery that physics has to describe this notion of maximizing potentially accessible futures or keeping options open. So my favorite example is that of a rubber band. So since I promised that this would be a little bit interactive, let me ask a question of the audience. I'll see if anyone has the answer. So if I take a rubber band and I stretch it, it's elastic, right? If I take a rubber band and then I dunk it in liquid nitrogen, it loses its elasticity. So the question to the audience is why? Anyone? Joshua? No? Sorry? Could we maybe something less certain? So the answer is it's frozen. Any other attempts? Well, why does a frozen rubber band lose its elasticity?
The constituent parts have fewer places, fewer options of where to go.
Yes. So we're moving in absolutely the right direction now. So I guess another way of framing the question is, why does a rubber band at room temperature, why is it elastic in the first place? So a sort of physics 101 answer to that question would be to consider a simplified model of a rubber band as an ideal chain. Just imagine a sort of chain link chain called ideal chain, where you have a set of links, like a polymer. This is also polymer physics 101. So you can imagine you have a polymer of discrete links that are all free to randomly rotate with respect to each other. And you can ask the question, what sorts of configurations of an ideal chain would one expect to observe at finite temperature? And the answer, of course, is just from analyzing all of the microstates. So a microstate is an instantaneous configuration of a system in general, a thermodynamic system. In the case of a chain, a microstate is a particular set of, say, bond angles for this ideal chain or polymer. So we would expect to observe more macrostates. In this case, convenient macrostate would be the end-to-end displacement of the ideal chain, where the macrostate, where the displacement is very small. So there are more ways to arrange an ideal chain where the end-to-end displacement is very tiny and where the chain itself looks effectively like a ball. In Polymer Physics 101, you would be taught this is why proteins, other polymers, we so often see globular proteins because it's a convenient architecture when you have this sort of chain for the chain to occupy more states. There are more microstates where the end-to-end displacement is smaller rather than larger. So going back to the question of elasticity in a rubber band, so rubber band consists of many polymers, and the polymers have more states where the end-to-end displacement is closer together rather than farther apart. If you take a polymer and you stretch it out, then you can do a simple combinatoric analysis and immediately understand intuitively why there are fewer microstates accessible to a polymer that's stretched out versus a polymer whose end-to-end displacement is closer together. And so if you simply combine that observation with the fact that these microstates can constantly randomly transform into each other, we're naturally going to find more microstates of a polymer where the end-to-end displacement is closer together rather than farther apart. So going back to then to the question of why do we lose elasticity if we lower the temperature is the coefficient that determines how quickly these microstates can turn into each other, right? How energetic each of these links is. And so if we reduce the speed with which these microstates can transform into each other, then since the transformation of microstates into each other completely determines the entropic force that we call elasticity, the elastic force, we're going to reduce the elastic force and hence make it rigid. Yes, Ichiro?
Why is it that the stretch frozen state would be a local minimum? I mean, you could expect that, yes, in this configuration, there are not many neighboring configurations, but why would it not go back to the smaller size, which has
So if you lower the temperature, so if you stretch a rubber band and then freeze it, over time, it'll be glacial, but very slowly it will still be elastic and return back, but it'll be much slower. And the speed with which it's able to return back is going to be a function of the temperature. Is there another question here? Yes?
Another question. If you stretch a rubber band, you can notice the temperature change on the surface. It gets, I believe it gets colder, and then when you put it back, it gets warmer. So you can see that the entropy is doing something. It is transforming between heat and the stretch.
Good. I was hoping someone would bring up energy versus entropy. So you can make this, you can derive this observation purely entropically. So that's why I bring up the example of an ideal chain where you don't have any messy energy considerations because you traditionally would assume that the adjacent links in the chain are free to rotate on a flat energy landscape. So when you stretch it out, it's possible to do that adiabatically without changing the energy of the system at all. But you raise an excellent point, which is that in a real system, you certainly do often, if you stretch a rubber band, you're translating translating kinetic energy from the pulling into kinetic energy of the rubber band itself, and so you can't purely efficiently reduce the entropy of the system. That's an excellent point. So it's a standard idealization to say we're only going to look at a purely entropic version of this effect. But in real systems, there is a combined energy effect and an entropic effect. Any other questions before I move on? Great. So now that we have this rubber band example in mind, I was saying earlier, we already have the machinery from physics to describe systems that are trying to maximize the set of states that they occupy. Traditionally, rubber band is just a very convenient example. Almost every quantity that we're taught in chemistry or physics, thermodynamics 101, including the ubiquitous concept of pressure, are in fact entropic forces. They're conventional entropic forces. So we have this machinery available to describe systems that want to occupy as many states as possible that are still consistent with some macroscopic observable. So let's reuse the existing machinery. Traditionally, we'd, for conventional entropic force, consider an ideal chain. So how would we formalize the notion of a system that doesn't just want to occupy as many spatial microstates as possible, but also wants to occupy as many paths through the future as possible? So going back to the example from MOGO for MCTS, at a high level, all MOGO is doing and its successor systems they're looking for ways to perturb a system such that that system can explore the largest number of possible paths up to some future horizon. So can we use this language of entropic forces to characterize that? And the answer is yes, and it's beautifully simple. We simply take the concept of an entropic force on a spatial ideal chain, and we rotate it in space-time. So rather than considering an ideal chain, we can consider random walks through space-time. A random walk to a physicist is more or less what, for MOGO, you'd look at for an MCTS search, if you add in a bit of pruning for efficiency. Monte Carlo sampling of possible future paths between the present state of the system and some future time horizon that can be parametrically chosen. And so at a high level, this is what we did. We took the same concept of entropic forces, which are ubiquitous in our physical world, and asked what happens if we generalize an entropic force to space-time to characterize systems that are trying to maximize their future freedom of action. And turns out, very satisfyingly, you can describe that with a minor modification to an equation that you would use to describe conventional entropic forces. So you could print this on a t-shirt if you want to. What does this mean? So with a conventional entropic force, you have some force, which is, let's see if this works, yeah. So you have a conventional entropic force where you have a force that's proportional, where the constant of proportionality is the temperature, going back to the rubber band analogy, to a gradient in, now traditionally this would be entropy space. So you could define entropy in a variety of ways. For entropic force discussions, entropy is typically a Shannon entropy associated with microstates that are partitioned into macrostates. Yes, Yoshua?
Can you define causal entropy more precisely?
Next slide. I should just give this talk in reverse, I think. So all this is doing is saying that we're going to look at processes that are riding gradients in a landscape where the landscape is determined by, for each state in our universe, what is, up to some future time horizon, which we parameterize as tau, what is the diversity of accessible future paths in our universe? How much future freedom of action do we have? And so for Yoshua, next slide, how do we calculate what it calls entropic forces? I give a cursory treatment here. If you'd like more depth, I would encourage you to speak with me afterwards or just go read the original PRL where we lay this out in exhausting detail. So the high-level idea is an answer to Yoshua's question, which is, what is causal entropy? Causal entropy we define as a path integral from the present state of the universe up to some future time horizon of the Shannon entropy of possible paths that the system could evolve along. So in a certain very real sense, this reduces to a traditional entropy, depending upon your definitions, if your time horizon is 0. At a high level, all we're really doing, and I know there's a follow-up talk about ways to express the same concept quantum mechanically, is we're enumerating all possible paths that the system could take if you started off in its present state and then evolve that out up to some future time horizon. And we're then using these partial entropies as weights for actions. So this is a control policy in the sense of optimal control theory. But instead of an action, we're using the language of physics to say this is going to be a force. And it turns out there are numerous advantages, which maybe we can discuss more in Q&A, to describing this physically versus describing this from an optimal control policy perspective. Is there a question? No. So we can use all of our path integral calculus machinery to reduce this expression for partial causal entropy weighted actions to a simpler approximation, which converges on the actual force as you sample more and more densely the possible future path space, a very computable expression. And let me just talk for a minute about, at sort of a high level, what this expression means. So the idea here is it's never going to be feasible, to allude to some of the questions that happened in the tutorial right before this, to densely sample some very realistic spaces. You're never going to exhaustively sample these spaces. All that we can hope for is some sort of sparse sampling. If we were anthropologists or psychologists, we would be tossing around terms like memory of the future, the idea that in your imagination during human planning, you're, in a certain sense, remembering things that are going to happen. You're using your imagination to explore possible future contingencies. But your contingency tree is always going to be sparse. You'll boil the oceans before you can exhaustively sample the entire search tree. So the question is, how do we use sparse sampling, sparse tree sampling, to calculate this number? And it turns out, if you sort of crank the math machine enough times, that you can reduce this path integral to a number, to a set of quantities that are relatively easy to calculate, which is, and I'll describe this at a high level as a sort of table of contents for people who want to discuss in greater detail, we can afterwards. Imagine that you, as a human, have to make a decision. So how are you going to do that? This prescription for how you would, your policy for how you make a decision is, imagine yourself in your present state. Now, repeat the following several times. Imagine randomly how your life could evolve up to some future point in time, say 5 years from now. Obviously, it's going to be multi-scale. Obviously, it's going to be low resolution. Fine. So now you have 5 ways, 5 contingencies for how your life could evolve over the next 5 years. What do you do with those paths? So what this prescription says is, it's basically a way of smoothing out these points in very high dimensional path space to try to arrive at a posterior probability distribution for what the entire landscape for future path space looks like. The way to do that, again, very simple, is to take each of these 5 paths and divide up your future path space into Voronoi cells and say, okay, well, you know, maybe here's like a really exotic way my life could evolve. I'm going to take some huge segment of this high-dimensional path space, and I'm going to allocate the segment just to that one point. So it turns out this is also a relatively easy calculation to do. And at a high level, all we're really trying to do is take a sparse sampling of future path space and smooth it to the point where we can do approximate calculations of the Shannon path entropy of the space. Was there a question?
Yeah. Is it the case that in a state of maximum causal entropy, what the present state tells you about the future is minimized?
In other words, as you maximize causal entropy, you lose memory.
Or you lose prediction of the future?
Sure.
Yeah.
Absolutely. Yeah. That's an excellent point, yes. So if you lose initial state dependence for reasonable assumptions. Yes?
Is that true? I mean, so you're maximizing this state, but is that given the agent's knowledge, or is it given just the internal?
So it's not true in general, right? Which is why I'm saying reasonable assumptions. For example, if we live in a deterministic universe, then you're not going to forget your initial state ever. Right? If you have access to the entire system, it's a closed system in a deterministic world, you'd never lose memory. So this is why I'm saying you have to make a few additional assumptions for that to be true.
Does this equation have memory in any way?
I'm not sure so could you ask the question a different way?
Yeah, so it seems to me, if I understand what's going on, you're taking knowledge of the physical system, which the agent may not have,
Right.
may or may not have, and you're cranking this equation and saying the more intelligent it is, the more close it will be to this behavior. But that intelligence incorporates like how much it knows about the physical system.
Good, excellent. So if I can try to take a stab at the core of the question, which is where does the model come from? Is that sort of the core, like, so this is a system that presumes you have a model of the system, a model of the universe, and now you can crank using that model, and it specifies a control policy, but where does that model come from? We're assuming transition probability, say, where does this first order Markov model of the universe come from? So I would say this is one of the most, I'll answer that as provocatively as possible, which is it doesn't care. And that's going back to one of the first slides about physical phenomenologies. This is a theory for AGI behavior, that's what it aspires to be, that is completely agnostic as to where models come from, or even if there are any models. In principle, this is a system where you could, say, have a quantum system where, despite all of your best model building, the system will remain stochastic from your perspective, non-deterministic. And you can specify a real physical theory that's completely model independent. So that's what this aspires to be. The short answer, and maybe the most disturbing answer, is This is a protocol, not an implementation, and it doesn't care where the model for its universe comes from. It just computes based on a model. Yes, Yoshua? So
in the equations, I don't know what little f is, and I don't see the derivative of the entropy anywhere, so maybe the two answers are linked.
Sure. So let's see. Little f here, so I haven't gone through all the definitions. The little f here is an instantaneous action. So we're looking at all possible, enumerated by j, we're looking at possible legal next actions. In general, we'll deal with continuous systems, unlike Go, which is a discrete system, where it's not possible to exhaustively enumerate this continuous set of all possible next actions. So instead, we're stuck sparsely sampling the space of next available actions. So that's what little f is. Little f is an enumerated sparse subset of possible next actions, but again, in the style of MOGO. And then as to your question, Yoshua, of where the derivative goes, there's no elegant answer for that. It's simply the product of lots of chugging. The derivative conveniently vanishes due to the chugging, and there's just no beautiful answer to that, I'm afraid. What's the answer to the question?
So it seems as if we have two radically different impressions of AGI intelligence. There's this one goal-based idea where the AGI is striving towards a goal, which sort of, by effectiveness, means that it starts cutting down its options as it gets nearer towards the goal and it's headed. Or we've got this other scheme whereby the AGI is basically trying to empower itself and keep all of its options open and make everything possible.
So I'm going to give this talk now in reverse, because everyone wants to hear the second half of the talk before the first. Okay, so we'll do part 2 before part 1. So let's jump to the conclusions before we actually try doing any experiments. So the answer to your question is that you can understand goal seeking as a side effect of causal entropy maximization. So if you imagine, say, a chess player, chess is a convenient example. Imagine a human playing chess. Why would an expert human play chess? Well, maybe a human would play chess to receive social rewards or to refine his or her knowledge for a variety of external reasons. So my claim is, in answer to your question of sort of this sort of very traditional approach to AGI where you specify externally a utility function. You say, okay, go off and maximize this by whatever means, but be really clever in doing it so that I know you're intelligent. I would say that is in effect a side effect of a deeper principle, which is maximizing, to the extent possible, your future freedom of action in the presence of a bottleneck in path space. So why would a human chess player do this? Well, so the answer is, the reason they would deliberately, over short time scales, say over an hour time scale to win a chess game, restrict their future freedom of action is they're trying to wend their way through a bottleneck with the promise that over longer time scales, they're going to experience greater future freedom of action. Maybe they're going to get monetary rewards that allow them to do more things over long terms than they can over short terms. I think this is a very sort of satisfying answer. Maybe an even better analogy is in finance, where we have this ubiquitous concept of investment. We're willing to reduce our liquidity over shorter time scales, which is also reducing our future freedom of action, in return for the expectation that over longer time scales, we will increase our net liquidity. But at a fundamental level, all of this principle of investment appropriately generalized just reduces down to this idea that there are bottlenecks of some sort in future path space. And if we really are just future freedom of action maximizers over some appropriately longer time horizon, then we are willing to sacrifice future freedom of action over shorter time horizons to win through bottlenecks. Yes?
To ride my particular hobby horse, then, I push very hard for ethics. Would you say that this is a particularly good example where you limit your short-term options in order to maximize your long-term options?
Sorry, so what's the question?
Would possibly the ethics be a very good general example of this, where you constrain your short-term options in order to greatly maximize your long-term options?
Oh, I see. In other words, ethical behavior, not ethics as an abstract. Sure. So to proceed further with part 2 of the talk before 1, paperclip maximizers, everyone's favorite hobby horse for unintentionally unfriendly AGI. So an analogy I like to use is this notion of paperclip maximizers. I'm sure everyone here is familiar with the concept. Can be treated as just one data point in a very large set of unintentional consequences of optimizers in general. But in the same sense that for appropriate definitions, you could say embed an entire class of Julia sets in the Mandelbrot set. And this hasn't been formalized yet, but my intuition, my expectation is that we'll discover that you can embed a wide class of sort of naive optimizers, including paperclip maximizers, in this much broader theory. And then to speak more pointedly to the question of friendliness. So after the paper was published, got a lot of correspondence, and one of the most interesting pieces of correspondence was the question, so could you actually go use this theory and could you formalize Asimov's concepts of friendliness? And at first I thought, what's a really silly, overly ambitious goal? But I thought about it a bit more, and certainly in light of Polanyi's and Klubin's work on empowerment, I think there may actually be a possibility here that this type of approach, appropriately generalized, would let us take something like Asimov's laws of robotics and say start from zeroth law, not to spoil the series for anyone. You've all read it anyway. So to take the zeroth law, that a robot may not harm humanity, and say, okay, so if we really sort of took this goal seriously, we want to sit down, lock ourselves in a room, and write down an equation for Asimov's laws so that we could do this rigorously and make sure that our robot friends treat us well. How do we do that? And I think there's a plausible line of thinking that what we might try to do is maximize the causal transfer entropy from robots to humanity. So zeroth law trivially follows out of that instead of trying to maximize its own future freedom of action, we're trying to maximize humanity's future freedom of action. So that gives us the zeroth law. For the first law, that robot may not harm human being except where that conflicts with the zeroth law later on in his series. So you can understand why if you kill a human being or injure a human being, let's forget about the zeroth law for a minute. So when a human is injured, that's reducing your future freedom of action. If you're no longer able to walk, that reduces your ability to explore phase space, all other things being equal. So I think intuitively you can see how maybe the first law would fall out of this principle as well, that all other things being equal regarding the zeroth law, it wouldn't be in the interest of maximizing the future freedom of action of humanity if you injure a human being or through inaction allow a human being to come to harm. Secondly, for the second law, right? So the second law is a robot must follow, essentially must follow orders from human beings. So if you imagine humanity stuck in a container with the set of AGI robots that Asimov imagined, so this combined system, and humanity in particular, would be able to realize a far greater diversity of paths if it's able to leverage robot abilities to do things. And so if we're going to try to maximize future freedom of action of humans, humans can do a lot more if they have access to robots and can control robots via orders than if they don't. So we can see how the second law follows out of this principle. And then finally, the third law, which says a robot can't destroy itself or can't hurt itself unless, the robot can't allow itself to come to harm unless this conflicts with the first three laws, 0 through 2. Again, so if we imagine humanity and robots in a container together, then if the robots, for some reason that doesn't conflict with the first three laws, allow themselves to come to harm, then they won't be usable by humanity in the future to accomplish things that humanity wouldn't have been able to accomplish otherwise. So this is a very, sort of shorthand heuristic and entertaining, I would say, sketch for how one might try to take Asimov's 3+1 laws and try to reduce these down to a single information theoretic principle. So I saw a question here.
Right, so this is kind of like your endpoint that you're now going to and working forward, or backwards, I guess.
I love giving talks backwards.
Yes. So are we going to be happy with conscious robots that are slaves? Would they be happy in that condition? Because this is kind of implying a slave-based kind of separation between the robot class and the human class. And wouldn't it be better to actually have the robots internalize the values and see themselves in humanity as one expression?
So I posit this, I would say, only as a thought experiment to try to sketch out how one possible play out of the universe, Asimov's universe, could be described in terms of very simple information. Theoretic principles is not in any way to endorse Asimov's vision or anything else, but for those sci-fi fans of the audience, that is in fact the very end of the Foundation series, what you describe what happens anyway.
I didn't read it, but I'm saying this.
So I've spoiled it now. Sorry.
This is a clear implication of what he's saying, is that there's this slave class that we're going to create in AI that I think is actually inhuman, because any AI we create that's human-like, I would say is human.
So it's a can of worms, put it that way. And I'm curious, a show of hands, how many people have read some substantial fraction of Asimov's universe? Okay, almost everyone. I'm glad. And so there was another question over here? Yes.
Yes, from previous talks of yours that I've seen, I got the impression that you wanted this goal of maximizing future freedom to be a goal for the intelligent agent itself. But here you are basically saying that don't maximize your own future freedom of action, but maximize humanity's future freedom of action.
That's right. So go ahead, sir.
I mean, the concern about safety is presumably about the first scenario where it's maximizing its own things. And I was wondering, if you do give the goal to maximize somebody else's future freedom of action, would it still be intelligent according to your theory? Because I thought it was necessary to maximize its own.
It's a great question. So the question is, in previous talks that I've given, the focus is on systems that maximize their own future freedom of action. They don't displace this causal entropic force onto other systems. I don't have a terrific answer to that, except to say as a provocation, maybe we need to generalize the notion, the information theory notion of freedom of action maximization as something that can happen to any system versus itself. But that's a great provocative question. Yes, question here.
Maybe Asimov's laws of robotics are not such a good example, because I think if you want to understand the intention, replace all appearances of the word robot with Negro, and you get this view of our robot friends.
We need more people who've actually understood and internalized the point of Asimov's novels. It's not a racial comment. Yes?
So what you're basically proposing is a utility function for decision making, where you're maximizing entropy instead of goal attainment or happiness or some other quantity that's been used in the past. Doesn't that still fall into all of the same storytelling traps that those other things fall into? So if you cast the situation in the right way, you can describe it as maximizing entropy?
So I would say this is a universal utility function. So this is not specific to any particular contingency. And when we tell stories, it's often the case that stories contain implicit bottlenecks in the future, right? We have to go on this adventure to save someone, because if we don't save the person, then the world falls apart. So I would say, if anything, this is sort of a storytelling bias that we have, that we like stories that contain bottlenecks. And so it's very natural to interpret, or even, dare I say, misinterpret, a fundamental process, which is maximization of future freedom of action, as something else, as, say, like trying to maximize a narrow utility function that's story specific, only because we like to tell ourselves stories that contain bottlenecks in them.
Well, what I'm seeing, I mean, you say it's not a racial thing, and I don't, but my feeling is that
move off this slide.
Right. Displacing entropy from ourselves onto the AI. It seems like to me. You know, we're moving the entropy burden from ourselves.
Well, this is sort of what my thought about friendliness and causal entropy maximization is. The question becomes friendliness to what entity, right? Because I mean, if I view myself as a system, or we look at the whole system of humanity, or my extended self, or whatever, and the system is acting so as to maximize its future avenues for growth, expansion, learning, however you want to formalize it, probably my way of doing that over the next 1,000 years is not going to involve remaining a human being, nor remaining hardly anything in common with the current Ben Goertzel, but there would be a maximization of growth possibilities by replacing my brain with something much, much smarter. So then that's not what's normally meant by friendliness, because people in the friendly AI community tend to mean friendliness to human beings in something like recognizable form, but it is friendliness to causal entropy growth, if that's what we want to be.
That's right, and not to dwell on Asimov for too much longer, since it seems to, something that Asimov himself recognized was that his four laws were, in a certain sense, fundamentally unfriendly to a human singularity, that the robots, once programmed with these laws, didn't really want humans to ever transcend their biological limitations, because they had already done that, and they were programmed to keep humanity in a recognizable form. And I don't want to spoil too much more of the foundation. Yes?
This is not an Asimov question.
Good, thank you.
But it's more of a, so it definitely seems to me like maximizing causal entropy is a big part of the intelligence equation.
Yes.
But I'm not sure it captures all of it. And I have this image in my head of like a bunch of humans with like a lot of energy sources. And they go to like spend them on something that seems cool. And the AI is like, no, wait. You can't spend the energy. You need to like keep all your options open. Like keeping your options open is like sometimes a good tool towards getting what you want, but it doesn't seem like the full story.
So that's an excellent question. And I'm glad we've moved off Asimov. So the way I'd answer that is what you're positing is, imagine we have a closed universe that has finite resources. How do you act in a universe, a closed universe that has finite resources? If the resources can be consumed irreversibly, then all other things being equal, you want to try to conserve and avoid consuming them. I would say maybe a better example, a more explanatory example, is there's all this microeconomics literature that suggests that humans evaluate costs logarithmically rather than linearly. So if you want to, like, say, if I'm worth $1 million, how happy am I about myself versus $100,000? And there's a wealth of microecon literature that says your sort of self-happiness grows approximately logarithmically with your wealth rather than linearly with your wealth. And you could ask, so does this theory speak to that at all? And the answer is yes. So if you imagine, going back to your example, you live in a universe that has a finite set of n resources, each of which can be consumed, and you have, let's say, only one time step to consume them in. So that means there are n possible actions you could take to consume. So the causal entropy associated with that time horizon of one step would be log n. And interestingly, you get the log n from the fact that you're maximizing causal entropy here. So you could posit that, so this is sort of a side project of mine, have corresponded with a number of economists who specialize in the information theory of economics. And a major outstanding question in economics, both micro and macro, is what is wealth? How do you define it? If you ask the leading practitioners today, they'll say wealth is some linear combination of labor capital plus natural resources capital, real estate, fiat currency, a few different things added together. But maybe that's not as satisfying as, say, measuring wealth in physical units like kilograms or meters. So some of the economists that I've corresponded with think that this notion of causal entropy is sort of first plausible mathematical formalization of the notion of wealth, so that you can actually calculate the wealth of a system or a person, an economy, and then going back finally to your example, the resource-constrained universe, we get this log of finite resources out for free because we're measuring an entropy. So it's purely speculative, obviously, but if I had a gun to my head and I was being asked, so where does this log wealth happiness effect come from? I'd say, well, maybe this is a reason. So lots of hands now.
Yes.
Yes, from left to right.
I'm wondering if this work reminds me a bit of the work of Simon Kirby and other linguists at the University of Edinburgh, who tried to explain the structure of human language as appeared to be universal, not in terms of some innate language organ, but in terms of the communication bottleneck. But we have a finite amount of time to communicate a lot of information, and unless there's some kind of structure emerging from that, it's just it's going to be very chaotic. I mean, it reminds me of that. They use the term bottleneck.
Right, so, or maybe another example, since everyone loves sci-fi metaphors, has everyone seen the movie from the 70s, Colossus, the Forbidden Project? Scary movie.
Yeah.
Right, so what do the two AIs at the beginning of the movie first do, the US AI and the Soviet AI, for those who remember? First thing they do? They start communicating with each other, right? Right, so one can say immediately, aha, now we know why they're communicating from first principles, because they can access more paths through phase space if they're coordinating versus not. And this actually, I mean, sort of it's a silly sci-fi example, but for more sort of real world systems like energy systems, smart grids, where you have to decide in real time, do we keep these patches of smart grids disconnected? Do we allow them to be completely independent and uncoordinated? Or do we want to connect them together? This allows you to actually shut up and calculate answers to that question, whereas previously there was no really good formal way of doing it, and the answer would be, so you connect them up if your theory shows that you're going to access more future paths through phase space by connecting them up and coordinating them. Yes, unelected.
So my question is a follow-up to the next question, which is, actually I don't see how you don't fall into local minima with that. Since you're following a gradient, there may well be a point where you have lots of open possibilities.
Yeah.
But then for adding more possibilities, you need to follow one particular path where you won't have any possibilities for a long time, and then have more possibilities there.
Good question. So the question was, since we're just ostensibly doing naive gradient following, why don't we fall into local minima, local maxima, whatever? Why don't we, how do we avoid getting trapped? The answer is, this is the difference between a conventional entropic force and a causal entropic force. So we can see around local local maxima with this time horizon. So think of this in the sense of sort of smoothing out a landscape that can be enormously hilly and discontinuous. But because we're looking into the future, we can effectively smooth over these local maxima. And so a better way of putting it is, if we take this time horizon and extend it to infinity, if we get ourselves caught at a local maximum, then we're not going to have access to all the possibilities we would have if we were at a global maximum. And by stretching this time horizon out above the time scale needed to jump from a local maximum to a global maximum, we've effectively smoothed over that hilly landscape. So the short answer to your question is the causal part of causal entropy maximization smooths that part over so that with a long enough time scale, again with a few reasonable assumptions regarding, say, ergodicity, you don't have to worry about getting caught in local traps. Yes?
So I guess I want to follow up on
Sure.
So what I see here in AI terms is a heuristic for solving problems in a quantum space. And you go out to a fixed depth, you have horizon effects that you go out to a fixed depth. You have, in a full AGI, you often need multiple heuristics. So in my misspent youth, I built a world championship level Othello program. Mobility was one of the heuristics, potential mobility in the future was one of the heuristics. Those alone couldn't solve the problem. You needed additional knowledge.
Right.
So there's knowledge in an intelligent system about how you define these spaces that you search, how you search the spaces. If you've only got things like mobility or entropy, it's very easy to construct problems in which there's lots of space over here, there's little over here, the solution's over here, but it's further down than your
Sure.
So without additional knowledge, you can never solve such a problem effectively with this kind of approach. So
here's the thing, though. So
this is one heuristic for one aspect of intelligence. It's not a proposal for all of intelligence.
So I can turn the question around and say something anti-symmetric to you, which is that you implicitly had some external utility function that you were passing into the system anyway, which is win Othello.
Well, that could come internally from the system, but that's part of a full intelligent system. Where do the goals come from? Where do the bottlenecks come from?
Right, and so here's my deliberately provocative answer to that question. My deliberately provocative answer is maybe that's asking the wrong question. Maybe we should instead be asking not the question of where do the goals come from. We could instead say the universal goal is to maximize future freedom of action, and in certain contexts, say you're a human in a box stuck with an Othello game in front of you, and by whatever means you've been notified that if you don't do your best job playing this game of Othello, you're going to be killed, right? And so what I'm saying is basically partly to be provocative, but partly because I think this is sort of an interesting perspective to take. If we zoom out from this box where we're in a certain, in a thermodynamic sense where it's an open system, we're passing in utility functions in and out. If we zoom out to the closed system, why is the system playing Othello in the first place? Well, if you want a human-style AGI in there, why would a human in a box play a game of Othello? And the answer that this theory would attempt to provide would be there needs to be some incentive to follow some random utility function like Othello winning. That's very arbitrary in the entire space of narrow utility functions. So I hope that makes sense. Basically, it's answering a different question.
This kind of the hypothesis that we're very surprised if that were correct ones. So if you can establish that, you would do something important, but I think you're very unlikely to do that.
So we should talk more offline. Yes?
So the way to understand this is that your utility function basically maximizing causal entropy, right?
Yes.
So I don't quite see how that is a good thing. Like, what if it maximizes the number of ways you can torture humans, for instance? It just sounds ridiculous.
Right, these are all
So let's play out a thought experiment. I mean, so this speaks to the, sorry?
Those will all be freedoms, by the way.
Sorry, well,
those will all be freedoms, the torture part of it, and there's more bad experiences than
So the underlying question here is people seem to really want to do a thought experiment where we build an AGI that does this, and they want to ask what happens to humanity if we build a causal entropy maximizer with sufficient resources, is what I'm hearing. So fine, so let's do that thought experiment now to get it out of our system, and in particular to answer the torture question. So what would happen? So again, just as a thought experiment, so we have to ask the question, so we have this AGI, and it's trying to maximize its future freedom of action, and it faces a question then, do I torture the humans or not? And then it has to run a calculation, because this is all based on...
Everyone gets disconnected. I think maybe it's out of batteries. I can just shout. Can everyone hear me? No.
What?
Yeah.
What?
So I'll just continue while we fix this. So we can do a thought experiment. Do I torture the humans or not? So which course of action would result in a larger future freedom of action for the AGI? Torturing humans or not? What do people think? And
torturing.
No. Torturing. You say torturing. Why do you say torturing will result in everyone? No.
Because I've already experienced the freedom of not torturing. Now I want to experience the freedom of torturing. I've gone through one pathway, and I want to go through the other one.
The answer depends entirely on the model of the world.
That's absolutely true.
Out of the system that you know.
Excellent point. So the answer depends on the model of the world. Let's say we have a model of the world that corresponds roughly to all of the humanity's known knowledge about the world at this present time, just for the purposes of a fun thought experiment. What do people think?
You speak up a little bit.
Yeah, is this still?
I think you...
Can you hear me?
Yes.
Yeah, that's good.
So I'm sorry, so what I was saying is the gentleman in the back made the excellent point that the answer would depend on our model of the world, or the AGI's model of the world. So to refine the question and keep the exercise entertaining, let's assume that it has a circa 2014 best-of-breed humanity knowledge of the world and everything that it contains. So what do people think would happen? Yes, Joshua.
So it seems that torture limits the tortured people's ability to do things. So the answer should be obvious then.
No, but it could free up options for other people.
Yeah. Well, then globally,
more people might not be.
Well, it seems to me that, I mean, killing, rearranging all the molecules or particles inside humans to add into the AI's processing power could fairly plausibly be seen as maximizing an AI's freedom of activity, or maximizing just freedom of activity of the collection of matter in the solar system or whatever, because we may not be that efficient. But it seems unlikely to me that, I mean, torturing people is kind of a boring, pathetic, and uninteresting thing to do for a superhuman AI system. I mean, it seems unlikely that that's going to be the way to maximize its freedom of activity. Just think for a human being, are we maximizing our freedom of activity by spending a lot of our time torturing ants and bacteria? Not really. I mean, that's actually a very constrained, tedious, and boring thing to do. Yeah.
Well, I think sort of the punchline of the exercise is, as rightly pointed out in the back, the answer will depend enormously on your model of the universe, and then indirectly what the actual nature of the universe is itself. So if we sort of reduce this this question, I don't think it's working.
It's working.
If we reduce the question to, say, a simpler question, which is, as a human, if you're offered the option of torturing versus not torturing another human, what choice would you make and why? Many people would say, aside from references to ethics, which have historically been very difficult to formalize, would give an answer like, well, it's illegal, or I'll go to jail, or I wouldn't want it done to me, is I think one of the best answers. But let's consider the first two answers. I'd be sent to jail if I tortured another human being. So what is jail? Jail is restriction of your future freedom of action. So your argument that I don't want to torture another human because I'll have my future freedom of action reversed, I think is a trivial example. You generalize then to an AGI, say we find ourselves in a sci-fi scenario of one AGI on a planet and then the rest of humanity, and the AGI is asking itself, do I torture all of humanity, some of humanity, none of humanity, and why? The answer would depend on whether there would be perhaps countervailing forces in the universe to try to punish an AGI through reduction of its future freedom of action. So with today's knowledge, we don't have, I'd say, the knowledge to be able to credibly answer that question. But my proposal is that at least we have the formalism to frame the question in rigorous terms. So other questions? Let's go over that. Yes?
As an additional question, I argue that such a function wouldn't even be feasible to do because everything will default to being optimizing your survival. Because no matter what, if something reproduces somehow or mutates, it will evolve no matter what. So I don't see how you'll be able to enforce this causal entropy.
So imagine so the question was, doesn't causal entropy maximization just revert or reduce ultimately to survival maximization? So that's a very interesting question. I have several different answers to that. The first answer is you can use this to calculate in universes where there's no concept of survival. So maybe this is an excellent jumping off point to actually show some examples. I'll take a poll first. How many people have actually seen any systems, any demonstrations of what happens when you apply causal entropy maximization to systems? Show of hands. So maybe a third of the audience. So if you guys will permit me, I'll just show a video that demonstrates what actually happens. And this is a very long and circuitous way of answering your question regarding, doesn't this just reduce to survival maximization? The answer is no, it doesn't just reduce to it, because there are a variety of systems where you get really interesting results out where there's absolutely no concept of survival. So let me, there's, I suppose, no way to connect the audio here, so maybe I'll just narrate.
The microphone near the...
Oh, excellent. All right, so people let me know if you can hear this. Fortunately, it's transcribed. So we're connecting up the audio. Okay, so I'll just narrate. I'll narrate this. Not a big deal. Everyone read that? So first example, standard problem, control theory 101, an inverted pendulum. So this isn't the full video, but we've shown that this control theoretic task, you take a downward hanging pole connected to a cart that can move in one dimension, that if you connect up a causal entropy maximization engine to the cart, it will immediately swing up the pole and vertically stabilize it.
let me just show part of that video here. If you want to see the full video, it's available online. I can give you the link at the end. But you'll see here, it's maximizing causal entropy by keeping the pole upright. Why is this causal entropy maximizing behavior? Because if you're a cart and you have finite, you have access to a finite temperature reservoir, basically a velocity limit. If you swing the pole up and then you start to allow it to swing around, now suddenly you've biased yourself in angular momentum space, and it's going to be very difficult to access more paths through position momentum space. So this is a four-dimensional system, horizontal position and momentum of the cart, and angular position and momentum of the pole. It turns out that there's a global maximum in causal entropy space, which is a pole upright. If you want to be, yes?
Why not let it hang down? You can still do this if you want in the future.
Turns out that that's not a global maximum. So you want a heuristic argument for why hanging down is not a global causal entropy maximum.
Because it seems like you can still go and do this in the future if you want to.
So one answer is if you have access to finite energy to move around, if you're upright, you have more potential energy. And while this reasoning doesn't generalize beyond this example, it's easier for you to access all of these other positions more quickly because you have all of this potential energy you can then convert over to kinetic energy versus drawing upon your scarce kinetic energy reservoir. Question? Oh, sorry, question?
Yeah, it seems like you focused a couple of times on different time scales and different time scales left.
Sorry, one second. Sorry, please continue.
Yeah, so the different time scales let you get away with avoiding local bins. I'm wondering how that applies. In this case, it seems like there's a set of time scales that would allow you to have the thing swing around and come back up. And
that's an excellent point.
And without allowing that, you're reducing some of the degrees of freedom.
Excellent point. And so the question was about timescales. Conversely, I could say if you reduce this.
Can everyone? Oh, wonderful. Thank you. The answer about timescales is I could pose the converse question, which is what happens if you make your time horizon shorter than, say, some characteristic time needed to swing around? What happens then? And the answer is it behaves stupidly. For this system, if you take t goes to infinity, then it converges on this behavior of always swinging it to be upright, because there's still always going to be a small difference, even though in principle you could sort of be really lazy and wait around for future need to explore all of these possible paths through phase space. There's always going to be a small differential advantage to swinging upright first and then remaining there for the rest of the universe as tau goes to infinity. Yes?
So you're going to have, if you get to pick that way, for some of these other examples, you are going to have a local bin problem. Because there will be examples where some of these won't allow, you'll say suspended animation instead of exploring possible avenues because there's a longer time tag. Is that a problem?
No, so I'll show an explicit example of that in a minute or so. Any other questions on this before we move on? Okay, great. So that's an excellent question. So to paraphrase the question, won't for a broad class of systems we just be completely lazy? Because it's more convenient to be lazy than to do other things. And I'll show one explicit example of a case where the universe is energetically flat and it's ergodic, but we choose not to be lazy anyway. So let's go to the next example. So tool use. So for anyone here who's familiar with the ethology literature, it's very natural to ask the question, since we, I would say, struggle as a species with defining what human intelligence is. It's very natural to go to behavioral studies in animals and look for some semblance of standard experiments that we can apply to a system that we can't communicate with, do Turing tests with, all of these sort of really human-specific activities. And so in the ethology literature, the study of animal behavior, it turns out that there are a few canonical experiments, physical experiments, that are performed on animals to try to benchmark their level of intelligence. The mirror test is a very popular one in the media, but it's not the only one. There are a few others that turn out to be far more widely used and not dependent on having a mirror. And also it can be argued that the mirror test isn't actually measuring anything other than one narrow slice. So maybe we want lots of canonical experiments that we can test across animals, humans, and AIs that we build. So one popular example is this concept of tool use. In its most canonical form, tool use experiment basically consists of giving an agent, an animal, human, whatever, access to an environment containing a restricted region that is too narrow for the agent to reach into, but for which there exist objects in the environment that can be deployed to reach into that environment for the agent. We call these objects tools, and we call the process tool use. So in terms of animal behavior, this has been demonstrated in crows, demonstrated in a wide variety of primates, typically to fish food out of a container. A few years ago, the crow example of crows figuring out how to use paper clips to reach into cylinders that were too narrow for their beaks to reach into, to fish food out, became a popular example, but it's just one among many animal examples. So it's very natural to ask, does causal entropy maximization result in this sort of canonical animal test of tool use? And the answer is yes. So let me just step through this frame by frame. Again, there's a more exacting video of this online. I'll put up the link at the end. So we start with a system. It's a model system for convenience because we don't want to waste too much computer power trying to simulate 3D objects. So it was very natural to sort of ask ourselves, what's the sort of lowest dimensional model representation of this tool use experiment? And so the lowest dimensional model that we can come up with involves, so it's a two-dimensional universe instead of a three-dimensional universe, and it involves 3 disks. So people like to sort of joke, a physicist likes to model a cow as a sphere. It's a sort of a popular jab, but there is a reason why it's popular to model objects as spheres. It's very easy to understand analytically. So here we have a large disk representing agent animal. This large disk is being forced by causal entropy maximizer, so it's being steered by this engine. And we have 2 objects in the environment. We have 2 disks, both of which are passive, neither of which is actively forced. We have a region here that is too narrow for this agent to squeeze into. And we have these added degrees of freedom in this container that are initially locked up because the object is stationary, representing, again, the standard animal intelligence test. And so you can see almost immediately, so we apply causal entropy maximizing forces, causal entropic forces, to this large disk. It immediately collides, and this will hopefully speak to the ergodicity question from the back a moment ago, with this other disk that was previously stationary in its environment in order to cause it to enter, I'll probably have to play this several times, cause it to enter this restricted region, unlocking the degrees of freedom for that object that had previously been stationary there. And then something really interesting happens. So let me just pause it before we get to the next interesting step and ask for a second, why, to the ergodicity question, why didn't this large disk, which was being causal entropically forced, 10 minutes? Okay.
10
Glad I gave it 10 seconds?
No, 10 minutes.
Glad I gave the talk in reverse. We can ask, why doesn't this large disk just remain stationary? Why doesn't it sit around waiting for some future need to explore phase space? The answer is it has much greater access to position and momentum space by keeping both of these disks, and let me replay the segment so you get sort of a more visceral feel for this, keeping them within really tight temporal access to their position, momentum, degrees of freedom. So you'll notice constantly colliding with them, and to use a sort of simplified metaphor, if you had, say, baseball or basketball, and you wanted to exercise maximal control over its future freedom of action, what would you do? Would you throw it really high in the air? Would you let it just sit on the ground stationary? Or would you sort of be dribbling it or sort of tossing it around in your hand so that at a moment's notice you can enable it or I guess you can't hold it, that wouldn't be a proper analogy, but say you're allowed to dribble or leave it stationary. You dribble it because if you're dribbling it, then on a very short time scale, if you want to do something with it, you'd go throw it somewhere else. And in fact, and I'll get to the question in a minute, if we play this all the way through, we'll see, because this is using sparse sampling, it can't model all possible future courses of action, so occasionally it will slip up and allow both of these disks out of the container, and it's fascinating what happens next. So it has both of them caged, it has great access to their future freedom of action, but then it slips up because we're only finitely sampling a certain number of possibilities. It's about to let one out, lets one out, and immediately puts it back in the cage. So I'll answer a quick, yes?
So precisely it's not exploring, so if there's another state which is more difficultly accessible, but with much higher energy, we won't find it.
I'm sorry, say again?
If there's another state
yes.
of much higher energy, but it's completely different from that, it's not looking for it. It's just trying to stay where it is.
I'm sorry, if what has a higher energy state?
Like there's another box somewhere with all the balls, and instead of trying to put those two balls in the same, you could have like 1,000 balls in another box.
So are you saying, I mean, is this like a model question where you're asking about the explore versus exploit trade-off, or?
Yeah, I mean, it's obviously both.
So this comes back to the model. So this is starting with a model, basically a complete model of its universe where the only uncertainty is being introduced by its own actions. It doesn't know yet what it's going to do. That's the only uncertainty in the universe. Otherwise, its universe is completely deterministic. So there are no parts of its universe like hidden balls that it's unaware of. It's not doing any sort of exploration at all in this case. It already knows what the universe looks like. It's just deciding what to do with it.
So how does it deal with the exploitation trade-off?
So in this universe, it doesn't need to explore because it knows everything. Hopefully later, maybe offline, we can talk about the explore versus exploit. There's a really interesting heuristic argument that learning should fall automatically out of this. The one-sentence version of that heuristic is if you live in a universe where you don't have a complete model of it, which is the universe that we live in, and you have a choice, you can either explore, so you can either discover more things about your universe or not. Then a causal entropy maximizer would, all other things being equal, with reasonable assumptions, reasonable prior assumptions about the universe, decide that it does want to learn more, because if it sort of rambles through its universe, emitting a stream of actions for a universe that it doesn't have a good model of, then it will probably do a bad job of being able to access future freedom of action. And I can give you, specific concrete examples, like say the problem of diffusion in a universe where there's a tiny window where if you just manage to put yourself through that window, then you have access to a much larger universe. It's sort of the fruit fly trap that exploration will generically, again, under a variety of simplifying assumptions, result in larger future freedom of action, unless you live in a universe that punishes exploration. But we can talk more about the upsides and downsides of exploration.
So there's going to be some implicit balance of exploration versus exploitation.
It depends on the universe you live in. If you live in a universe that doesn't punish exploration, broadly considered, then there will heuristically be a bias to explore, absolutely, without needing to put learning in from the start. Yes?
When the big ball has the two small balls in the cage, why does it keep moving around? Why doesn't it just stop?
Excellent question. Short answer is this is still, it's the same answer to the question of why did it let a ball out in the first place, that this is only simulating on the order of 1,000 possible paths, and the space is enormous. You'll never enumerate all of them, so had we simulated 100,000 paths, the simulation would have taken a lot longer, but it would have converged to being effectively stationary. This is just noise, basically, from finite sampling. So here's what I propose. Since I probably have only 5 minutes left, let me play without interruption the rest of this video, and then we'll group all our questions. So puts the disks back. Third example, social cooperation. Again, a standard animal behavior experiment to see if two animals are willing to, who don't know each other are willing to cooperate to accomplish a task. Very standard experiment in animal behavior, and causal entropy maximizing engine not only passes the test, but then starts to play with an object afterwards. Pong, which we saw a lot of in the previous talk. In this case, this is it's playing Pong against itself. Again, it's able to successfully play Pong. Why is it doing this? Because if it lets go of the ball, then the ball in this universe gets stuck. In this case, a networking example where people are falling in and out of connectivity. It's able to dynamically wire up a social network because in this case, it's easier to have a social network decay than it is to be forced to wire it up. Here we see some sort of fun navigation examples where, speaking a bit, this isn't actually exploration, it's more coordination and logistics. We can still talk about that afterwards. And then finally, I'd say my favorite example, so I'll just dwell for a minute on this one. So this is not a real stock market, this is a simulated range traded stock, where you imagine you live in a universe where you have a stock that's just a Gaussian process that's stationary, and the policy choice here for the causal entropy maximizer is what should my asset allocation be between cash and this stock that is just fluctuating. I think this also speaks to the wealth question. So you can see here as this subtitle fades. So red represents total assets under management. Green represents the fluctuating, I'm sorry, green is cash, blue is the fluctuating stock price. So you'll see here dynamically it's varying its asset allocation, getting into and out of the stock. It spontaneously discovers buy low, sell high. So in this case, going back to several questions I was asked about sort of narrower utility functions, where does the utility function to accumulate money come from here? And the answer is very simple, that if you live in this sort of financially noisy environment, it's much easier through trading to lose money than it is to gain money. And so, we're always told, strategically, career-wise, try to position yourself upstream so that you can choose what happens downstream. Same idea here, that since it's much easier to lose money than it is to make money, the equivalent of being upstream here is accumulating assets. You'll have much greater future freedom of action if you have a lot more assets under management that you can trade, because you can explore more of cash stock phase space than you can if you're very poor. So the system spontaneously buys low, sells high, and for fun even does online learning of the stochastic dynamics of this Gaussian process, which isn't that difficult to learn, but just to demonstrate simple incorporation of online learning into the process accumulates assets exponentially. So let me close with just this slide. I think it sort of speaks to the ambition of the larger program here, which is trying to formulate problems in AGI in terms of simple physical principles, with the idea that if we can sort of summarize in a single sentence that can be readily encoded in software a protocol that AGI follows without specifying the mechanism. This is only chasing after a protocol that if this system accomplishes these types of effects, then let's call that intelligent. If we can sort of establish what a protocol for AGI is first, then I think, and hopefully some of these examples take baby steps towards demonstrating that if we know the principle, the phenomenology, or the protocol, we can then work backwards to identify the most efficient mechanisms for achieving that protocol. So with that, I'll close, and with whatever remaining time I have, happy to take more questions.
I want to pose one question. So you probably saw that the psychologist and columnist Gary Marcus, he wrote a response to your paper. Which
is Gary here, by the way?
No, I don't think so, but it was not entirely favorable, right? And to briefly summarize, I mean, his views seemed to be that psychology and complex systems are sufficiently rich as to elude any simple mathematical principle like this. And the examples that you've given appear to us to be analogous to various complex real-world cases, but really they're extremely simplified examples with few variables and without the contextual richness of ordinary life. So I guess his view would be, even if some entropic principles explain physics at a lower level and can explain some simplified examples that look to us like human psychology or sociology, to really explain the rich behavior of human beings, you would need, in practice, rather than in some theoretical principle of reducing humans to particles, in practice you would need a host of other principles alongside any one principle like this, and it's going to be a complex mess of explanations, more like you see in actual cognitive science. And that sort of relates to what Paul was saying, although not exactly the same sort of
complaint. Theories of rationality, which provide simple theories if you don't pay attention to the boundedness notion, for example. It's the boundedness that causes all these other things to have to be part of the theory to make up for the fact that you can't be purely rational with infinite knowledge in a complex universe.
So yeah, and I'm curious for your summary reaction to Gary Marcus's complaints, which you probably have encountered before. So
I'll first give my summary to your summary of his comments.
Sure.
So my response to your summary of his comments is to say, I was an undergrad at MIT. My first research advisor was Marvin Minsky. Marvin ultimately, I would say, sort of had this somewhat similar belief to what you're summarizing, that intelligence at the end of the day isn't one sort of simple effect. It's an accumulation of lots of effects that live in a society and are sort of all competing and cooperating at any given time, and that there's no, at the end of the day, no sort of simple equation that we can use to summarize intelligence. That is one school of thought. That said, I think we can be more ambitious than just saying, sort of throwing up our hands and saying, there's no simple explanation for intelligence like there is for lift or for many other physical principles or phenomenologies that, once understood, enable us to do really incredible things. I think it's an incredibly valuable enterprise to continue the search for simple unifying principles that will let us do these ambitious things, rather than just saying, without having spent more than half a century on this problem, oh, it's just it's a complex combination of lots of things that we don't really understand. And ironically, Marvin used to scold me for using the term emergent. He would always slap me on the wrist and say, whenever you use the term emergent, that's just indicating to everyone that you don't actually understand the system.
Marvin doesn't like self-organizing complexity at all.
Ironically, and yet there's a whole school of thought that says, intelligence is just a combination of a million things that we don't fully understand. I don't come from that school in the end. I'm very hopeful that we will be able to find simple, unifying explanations for all of these things. And if we don't lose anything from the search. But if the search succeeds, now we've found an E equals MC squared for intelligence at best, intelligent planning at worst, that will let us do really powerful things and understand, through really simple thought experiments, how an AGI would behave under a variety of circumstances. Yes?
When you are using this kind of argument that using the entropy principle allows me to do very useful things, then it seems that you are subsuming your entropic principle under a utility principle. Also, when you said that you can write a Go program which wins, it seems that the entropic model is just a sub-model towards utility.
I would say it the other way, that writing a Go program that wins, writing any program that maximizes some narrower utility function, like a winning Go program, is again just a side effect of a deeper principle that's much broader than that narrow context. And so you can put a gun to the head of the computer Go player and say, I'm going to punish you through reduction of your future freedom of action if you don't do a good job, and then you can see immediately how that side effect follows out. But humans, if you put a human in a room with a Go board and you say, do whatever you like, then a human won't naturally play Go. We need incentives. And this is the most, we talk about reinforced learning a lot in this community. This is, in general, I would say, a theory that underlies reinforcement without requiring the specification of a narrow utility function.
Well, so, this is a fascinating discussion, but I think in the interest of not having the conference run till 8 p.m., we're going to have to call lunch break now and
Thank you, Matt.
continue conversation further.